the indefinite integral, since we have both of them, they're both like related yet different, especially in what they mean. So you should see in OneNote, I kind of created this table. And we're just going to talk kind of briefly about like review again what the indefinite looks like, and then comparing that to, of course, the definite integral. The indefinite integral was one that we had already talked about. It was what was on your quiz. We know that the indefinite integral basically looked like we had the integral sign of some function with respect to dx. What did it mean? When we're looking at the indefinite integral, it told us to find all antiderivatives of f of x. And if we're finding all antiderivatives of f of x, we know that those answers were going to be in the form of f of x plus c, and I am using that capital F of x there to, of course, represent the antiderivative. And we know that was basically the process of undoing and a function, basically kind of like undoing the derivative process. That's what I'm trying to say. So today what we're going to compare it to is the definite integral. Definite integral definitely has some of the similar things. It does have an integral sign. We will be integrating a function still with respect to dx. What makes it obvious to us that it is going to be an indefinite integral is we are going to have a starting point and an ending point. So I'm going to write that as the integral from a to b. Those numbers do have names. That a we are going to call the lower limit of integration. And the top one we are going to call the upper limit of integration. I also like thinking of the lower one as the starting point and the upper one as the ending point. So we have the starting point and the ending point. And so then what does this represent? This is kind of like the big idea, probably one of the most important things that we'll kind of connect this to for this semester, really. And we're going to describe that the definite integral, it is asking you to find the net area from the curve to the x-axis from x equals a to x is equal to b. Some key words that I'm going to focus in on that. We are going to be kind of focusing in on the idea of this net area. And then, of course, you can see the starting point to the ending point, and it's the net area to the x-axis. Connecting this to some things that we did first semester. So like first semester, I say like the big ideas, we have like the derivative, and we're going to think of the derivative as a slope. This semester, we're going to think of the definite integral as something. And whenever I say the definite integral, we're going to think of that as the area. More specifically, we're going to think of it as what we call the net area. So what will our answer to a definite integral look like? The answer to a definite integral will be just a number because it will be representing the area. We're going to talk about the definite integral and kind of finding it three different ways for this topic. We'll look at finding it geometrically, we'll look at it algebraically, and then we'll also look at it kind of like with just the arithmetic and kind of logically. We will eventually build and see why this is the area and how it just kind of works out that way. I think like when you think about it, if you're the type of person to think about these things, like in one direction, we have this math operation, like taking the derivative, and it's going to be representing the slope of a line. But when we go back in the other direction, it's representing an area. And I don't think most of us would think of area and slope as being very closely related, but through calculus, they kind of are. So the first way that I like looking at the definite integral, and I think the way that makes the most sense, is using geometry. So I have this kind of function right here. I should have labeled it, but this is the function f of x. I chose this function because like it is a piecewise function, but it's all built off of like in some ways like building blocks of shapes that we know. And so when we look at a problem like this, when I see the integral from 0 to 4, that literally means, hey, find the area from the curve to the x-axis from 0 to 4, starting at 0 and then ending at the 4. So when I'm looking at this problem, like this first one, the definite integral from 0 to 4, it is just that triangle. If the definite integral is area, well, the area of a triangle is 1/2 base times height. Don't have to simplify it. I'm going to and get the definite integral for that is 4. And again, how we're kind of relating this is the definite integral, the net area, the exact area under the curve. So we're no longer going to be approximating. We are just doing the net area. And we can do that for any starting point or ending point. So like the second region, we're starting at 4 and ending at 12. That would be the semicircle region that we want to find. Again, any geometry formula you've learned can show up. We know that the area of a circle, or hopefully we know, is pi r squared. If I'm doing a semicircle, then I just want half of that. So like the definite integral from 4 to 12 would be 1/2 pi, and then the radius of this would be 4. Again, I'm okay if you leave your answer like that. 4 squared is 16 divided by 2. The definite integral would be 8 pi. From 12 to 20, so if ever we have a figure that's like not just one shape, definite integral is the exact area, so we can just kind of divide it up into a bunch of shapes that we know. I see a triangle, a rectangle, and another triangle. You might divide it up differently, but you just want to find shapes that you know the area of. So what's the definite integral from 12 to 20? Well, I have like 1/2 base times height plus that rectangle with a base of 8 and a height of 2, and then that triangle 1/2 base times height. Again, could leave your answer that way. I'm going to simplify it just to make my math a little bit easier for that last problem. And we do see we have 2 plus the 16, but that's not right because I can't count. That rectangle doesn't have a base of 8. It has a base of 6. So now that I've counted, we have 2 plus 12, which is 14 plus 4. The net area is 18, so that definite integral is also 18. Also can do some like integral arithmetic, like if I just want to do the integral from 0 to 20, I'm not going to waste time recalculating everything because I can just do the integral from 0 to 4 plus the integral from 4 to 12 plus the integral from 12 to 20. So big idea, when we see a definite integral, we're going to think of the definite integral as area. Questions so far? All right, so I'm going to kind of keep continuing with this idea of just looking at area because we know that sometimes functions can look differently. The next example I want to look at is when the graph goes below the x-axis. Like we know not all functions are always going to be above the x-axis. Big idea that we're going to add what we've looked at is when we are moving forward, and when I say moving forward, I'm talking about like zeros over here, and we're moving along the positive x-axis in kind of like a positive motion. When you're moving forward, area above the x-axis is positive. And if you're moving forward, then area below the x-axis is negative. So if I'm moving forward on this graph, like if I were finding the integral from, say, 0 to 8, I call this function f of x dx. From 0 to 8, we'll be starting at 0, ending at 8. So we have this forward motion happening. It's above the axis, so I know that this would have a positive area. And it's that same semicircle, 1/2 pi r squared. 16 divided by 2, it gives you 8 pi, as expected. What's different now, what we're going to add to that is if we are moving forward, but we are below the x-axis. So if I am starting at 8 and then going to 12, All of that is below the x-axis, so we're going to consider that to be a negative area. I chose the same semicircle here, so this net area would be called negative 8 pi, and that's what the definite integral would be equal to. Why we call this net area, we'll see an example like if I put those two together. If I did the definite integral from, say, 0 to 16 of f of x, that would be all the area starting at 0 and ending at the 16. Well, the first part of that was 8 pi. The second part of that was negative 8 pi. Both of those cancel out completely, and you're left with a net area of 0. And I think that makes sense now. Basically, all that positive area is canceled out by all that negative area. So the net area from 0 to 16 would be 0. Questions?
So the net area is of the whole function, if it's from
The whole
0 to
function, well, net area is wherever you're starting and ending at. So like this last one, it was the net area from 0 to 16.
Would the net area from 0 to 8 be the 8
Would
pi?
be 8 pi, yeah. We're just calling the answer to a definite integral the net area.
Okay.
And I'm saying net because that's going to be different from what we'll say eventually, like the total area. The total area will kind of ignore the whole positive and negatives, but for us in this unit, we're going to stay in kind of like talking just about the net area. So I mentioned moving forward, area above the x-axis is positive, area below the x-axis is negative. Well, what happens if, say, we are moving backwards? So I chose these 4 integrals. The first 2 were moving forward. So like I am starting at 1, ending at 5. So I'm going from 1 to 5. So on the graph, we're starting at 1, ending at 5. Same thing from underneath it. You're starting at 1, ending at 5. As long as you are moving forward, the area is going to stay true to where it's located at. Area above would be positive. Area below would be negative. And this is a triangle, so pretty easy to find. 1/2 base times height, net area of positive 5. This bottom triangle, it's below, so its net area would be negative 5. Now, if I flip the limits of integration, that will be in these second 2 problems. This is kind of will be the new stuff. If you are moving backwards, the sign of the area will flip. So for example, in this first one, I'm going from 5 to 1. 5 is the bottom one, and 1 is the top one. So you're starting at 5, moving backwards to 1. When you're moving backwards, what was a positive area would become a negative area. So this definite integral would become negative 5 instead of positive 5. Same thing would happen if you have a negative area. If you're going from 5 to 1 moving backwards, what was a negative area would then become a positive area. So this definite integral would have positive 5 as its answer. So we are going to kind of attach the definite integral with kind of net area, but we are going to also have to take into consideration that area could be both positive or area could be negative. So that's how we will look at it geometrically. Like if we had the graph in front of it and we could divide it into shapes, then we know that we could easily find the area. We also want to talk about how we'd find it when given just the equation of the graph. So to skip ahead a few slides, don't need to go to it now. I just want to show you the picture. But if I like this is the definite integral from -1 to 2 of 3x squared minus 4x plus 2. What this means mathematically is we want to find the area starting at -1, ending at +2. So when we're looking at a problem like this, we don't have a geometric shape that is equal to this. Like this is clearly not regular geometric shape. We can't just easily divide this up into rectangles. Like we can approximate it, but we want to talk about how we can find the exact area. And how we do that, I am going to kind of skip a slide and go back to it. We're going to go to this slide that says the first fundamental theorem of calculus. You can tell by its name that it is a super important formula. Like, we're going to use it all semester long. And basically what it tells us what to do is it tells us how to evaluate a definite integral. And the way that we're going to evaluate it, some things that are going to be similar to indefinite integrals. We're still going to have to find the antiderivative. I'm going to use capital F of x to kind of represent my antiderivative. But we're not going to worry about the plus c. I'll get into that in a second. And to plug in a definite integral, I'm going to use a vertical bar just as some notation, because we still need to evaluate this for a and b. So an integral is going to be different from a derivative. Like for a derivative, we know that we plug in two values, or excuse me, for one value. For an integral, we're going to plug in two values. And then the most important part is going to be the order that we plug. When evaluating an integral, you're going to, after you find the antiderivative, you're going to plug in the top minus plug in the bottom. This only works as long as f of x is continuous on that interval from a to b, which for us in AB calculus, that will always be the case. We don't really deal with the cases where it's not continuous until like Calc 2 or Calc BC. Another way that we can rewrite this formula is with like a derivative. I know that integrating a derivative, integrals undo a derivative, so the integral of g prime would be g. I'm going to use a vertical bar to show that I'm still plugging it in. And then we will plug in the top value minus plugging in the bottom value. We'll get into a little bit later why this works the way it does. I think it's hard to kind of think about in terms of area right now, but when we go back and start talking about like position, velocity, acceleration, it makes sense when we plug it in this way. Any questions on that formula? All right, so let's look at examples. I'm going to go back to that first example I kind of had drawn out. So looking at this one, I have the definite integral from -1 to 2 of 3x squared minus 4x plus 2 equals dx. And again, what this means is this is asking us to find the exact area starting at -1, ending at +2. So that kind of shape I have in that weird mustard color, we're going to find the exact area of that figure. Step 1 is to find the antiderivative. So that's going to become x cubed, 3 divided by 3 is 1, minus x squared, 4 divided by 2 is 2. The 2 becomes 2x. I need to evaluate this from -1 to 2. Don't need to worry about the plus c. And then to evaluate a definite integral, we are going to plug in the top number. So I have 2 cubed minus 2 times 4 plus 4. Minus plugging in the bottom number. Well, -1 cubed is -1, minus -1 squared is +1. Can leave your answer like that. I'm going to simplify it just because I think it will make it a little bit more obvious what we are finding. So that's first kind of is going to have 8 minus 8 plus 4, which is 4 minus a -5, and that is equal to 9. And again, what this represents, that 9 is literally the area of that figure right there. So you can imagine how powerful this can be. Like now, no longer will we have to just rely on like knowing the area of a triangle or a rectangle, but literally any shape that exists, as long as we can match some function to it, we can find the area of it. Which also has lots of other applications even outside of the world of just talking about area. Questions on how I did all that?
Yeah, so did you just plug it in?
Mm-hmm. Plug in the top minus plug in the bottom after you find the antiderivative.
So order matters, right? So you do
The order definitely matters, yes.
And then the bottom.
Correct.
Okay.
And why the order matters, like just to kind of expound on some things we did, like if I flip this integral and did it from 2 to -1 of that same function, pulling some things together that we already know. We know that if I'm moving backwards, this area above will be negative. Well, if I flip the order of integration, then that 9 would become, instead of a positive 9, it would be a negative 9. Also, just want to say why we don't need to worry about the plus c. Like, technically, all antiderivatives have a plus c. So, like, if you put a plus c, I wouldn't mark it wrong. But what ends up happening is when you plug in the top, you have that plus c, minus plug in the bottom, there's your other plus c. Well, c minus another c is going to cancel out. So that's why we don't need to worry about the c's when we're doing the definite integral, which is different, of course, than when we're doing the indefinite integral. Marcus, you have your hand up. What's up?
Yeah, when you find that, is it the absolute area or is that just like the net area?
It is still the net area. For this one, it is the actual area because the entire graph is above the x-axis. So we didn't have to worry about any like negative area taking away from the positive area.
Yeah.
So go ahead and try the second one for me. This one, so it does some trig. You will need to know your unit circle, of course. But I had the definite integral from negative pi over 4 to pi over 3. I've already graphed secant for us. Of course, we can do this without the graph of secant. So this is literally the area that we're finding. Again, you do want to make sure you show proper notation as you're working on it. Like, you do have to clearly show the antiderivative. After you find the antiderivative, use that vertical bar to still show that you're plugging in some values into it. And then when you plug it in, make sure you do the top minus plug in the bottom. Don't need to simplify your answer, but I do want you to evaluate trig. So take a moment to try that one for me. So pretty straightforward. The antiderivative of secant squared is tangent. Again, that's coming from our derivative rules. The derivative of tangent is secant squared. And then plug in the top. So we're going to plug in pi over 3 first, minus, and it will always be minus. Plugging in the bottom, tangent of negative pi over 4. Using my unit circle, tangent sine over cosine, so the tangent of pi over 3 is root 3. The tangent of negative pi over 4 is negative 1. So this one, again, the whole area is above the x-axis, so this would be the exact area of this kind of figure. The exact area of that would be root 3 plus 1. Questions on evaluating the definite integral? All right, I'm going to do one more problem for today, and then I'm going to save the rest of them for tomorrow. The one other problem I want to do today is sometimes where we have to figure out the limits of integration. So I have find the area of the region enclosed by the graphs of y equals 8 minus x cubed, x is equal to 1, and y is equal to 0. So we know that in this class now that when we're finding the area, we are going to have to use a definite integral to do this. In calculus, so both for my tests, the quizzes, and the AP exam, you always want to show your setup in order to maximize the points you're going to earn on the problem. So if we're finding the area, we do want to clearly show the definite integral that we're starting out with. So I know I'm going to have like an integral sign. I'm integrating this with respect to dx. Probably going to be 8 minus x cubed in there. I'm going to leave it blank for now. But we need to figure out what this region looks like. Like it says this region. And this region is bounded by 3 graphs. It tells me that we are bounded by y is equal to 8 minus x cubed, x is equal to 1, and y is equal to 0. Now, problems like this on the AP exam, same thing for me, is going to be something that's no calculator. So you would be expected to know what these graphs look like and be able to figure out what the region looks like without a calculator. Some of them hopefully are a little bit easier for you to figure out. For example, x equals 1. We know x equals 1 is just a vertical line through 1. So it will look something like that. Again, I'm just drawing a sketch, not a perfect graph by any means. Y equals 0, that would be a horizontal line. Y equals 0 would be just the horizontal line on the x-axis, which makes sense for us now since all of our areas between the curve and the x-axis. And then we have this last one, the graph of y is equal to 8 minus x cubed. So again, I'm going to use my knowledge of my parent functions to do this one correctly. I know that y is equal to x cubed looks like that kind of S-shaped function. So if I'm comparing that to y is equal to 8 minus x cubed, two kind of prerequisite skills happening here. That negative we know is a reflection, and then the 8 in front, that's a positive 8. So I know this graph is moving up by 8. So 1, 2, 3, 4, 5, 6, 7, 8. And I know it's been reflected, so instead of being kind of like an increasing S, this would be some sort of decreasing S. So then when I'm looking at the region, we're looking at the regions as bounded between those three graphs. The region we're looking at would end up being this, not really triangle, but three-edged figure. So that is the area that we want to find. So if I'm looking at this one, I can see that this region is starting at x is equal to 1. That was pretty easy to fill in. The curve that we're looking at is, of course, x minus 8 minus x cubed. What we're missing, though, right now is this upper limit of integration. So we want to figure out where this area region is ending at. So I just did a whole lot of talking. Before we find that question mark, any questions on anything I've done so far? All right, so let's talk about how we can find this kind of upper limit. So I can see clearly it is starting at 1 from that line. And we have all, again, this area that I highlighted. We want to figure out this point right here. Well, that point is where the graph of 8 minus x cubed is intersecting the x-axis. How do we find the x-axis of a curve? The x-intercept of a curve is we just want to simply set it equal to 0 and then solve. So I would have 8 is equal to x cubed. The cube root of 8, x would be equal to 2. So I know that this coordinate right here is really 2, 0. Notice I don't really need to know this upper one where they're intersecting because we're just talking about where this area starts at on the x's and ends at on the x's. So we are integrating this graph from 1 to 2. And then we can just easily go ahead and find our antiderivative. So the antiderivative will be 8x minus 1/4 of x to the 4th. Don't need a plus c from 1 to 2. And then plugging in the top minus plugging in the bottom. And you could simplify it. I'm going to be lazy and not. That would represent the area of our region. Questions?
Where did the 2 come from again?
The 2 came from because this function I did in black, this y equals 8 minus x cubed. I need to find where this region stopped at, and where that region stopped at was the x-intercept on the curve. So to find the x-intercept, I want to set the function equal to 0 and then solve. So I know that this function is crossing the x-axis at 2. So I know that this region started at 1 and is now ending at 2.
Okay, thank you.
Any other questions? All right, so I'm going to stop there today. Tomorrow's notes are much shorter. We're going to do the integral arithmetic slide I skipped over. And then we're going to do just one more example, find the area where we have to find the intercepts. I'm going to save the calculator example for Unit 7 just because it honestly fits better there to not add extra stuff in this unit. So I'm not going to worry about the calculator for now. Your assignment that I want you working on, so we're past the quiz at this point, you can go ahead and start working on homework number 3. Homework number 3, so I have 8 through 44, multiples of 4, and then I chose random 44 and 48. That's the integral arithmetic ones that we haven't quite learned yet. This second half of the unit, there's just 2 topics. We have definite integrals, and then what we'll do after the long weekend, U substitution. The test is going to be on the 27th of this month. So your first goal is, of course, start working on homework 1. If you want to start doing quiz corrections, you can. I haven't posted the answer key yet, but I will have that posted relatively shortly. During office hours, I will start posting your grades in Infinite Campus and all that. So that being said, I am going to go ahead and end this live session. Thanks for joining. If you're good to go, then I will see you tomorrow.